Physics often feels like an insurmountable mountain, a labyrinth of complex equations and abstract ideas that seem deliberately designed to be inaccessible. Many of us look back on our school days with a faint sense of dread, recalling physics as a subject of confusing formulas and seemingly pointless problems. But what if this difficulty is not a feature of the universe itself, but a failure of how we approach it? What if physics is not a collection of disconnected rules, but a single, magnificent story waiting to be told? This story is the greatest detective novel ever written, and its pages are the cosmos itself. To begin reading it, we must start with the man who provided the first truly coherent chapter, Sir Isaac Newton. His work did not just answer questions. It taught humanity how to ask the right ones, revealing that the language of the universe is written in mathematics, and that this language is far more intuitive and beautiful than we have ever been led to believe. Imagine two worlds. In one, an apple falls straight down from a tree. In the other, the moon travels in a graceful, endless arc around our planet. For millennia, these were considered separate phenomena. The earth was a realm of change and imperfection, while the heavens were a domain of perfect, eternal, and mystical motion. The idea that a single, simple force could govern both was unthinkable. Newton's genius was not in watching an apple fall, but in daring to ask a revolutionary question. What if the force that pulls the apple to the ground is the very same force that holds the moon in its orbit? This question shattered the ancient divide between heaven and earth. It united the cosmos under a single set of principles. With this insight, Newton gave humanity a powerful new tool, the ability to predict. He showed that the universe is not capricious or magical, but orderly and understandable. The movement of planets, the path of a cannonball, the ebb and flow of the tides, all could now be calculated, modeled, and foreseen with stunning accuracy. This was the dawn of modern science, the moment we realized that nature speaks in a consistent dialect, and we could learn to converse with it. So, why does this feel so hard to learn? The problem often lies in translation. We are taught the mathematics, the vocabulary, and grammar of this cosmic language without ever being told the story it is narrating. It is like being given a dictionary of Italian and being expected to appreciate an opera without ever hearing the music. We memorize F equals ma, but miss the sweeping epic it describes. That force, mass, and acceleration are characters in a universal play about action and consequence. Newton's 3 laws of motion are not just formulas to be plugged into a homework problem. They are fundamental statements about how reality operates. The first law, the law of inertia, tells us that objects have a kind of cosmic laziness. A thing at rest wants to stay at rest, and a thing in motion wants to stay in motion, unless something bothers it. This something is a force. Think of a hockey puck gliding across a perfectly frictionless ice rink. With nothing to slow it down, it would just keep going forever, a testament to this persistent state of motion. This isn't just about pucks, it's about planets. Earth is that hockey puck in the vacuum of space, and it keeps moving not because something is constantly pushing it, but because nothing significant is stopping it. Now, what happens when you do bother an object? When you push that hockey puck? This is where Newton's second law enters the stage. It establishes the relationship between the push, the object being pushed, and the resulting change. Force equals mass times acceleration. In simpler terms, the harder you push, the faster it speeds up. But also, the more massive the object, the more stubborn it is to that change. A gentle shove will send a shopping cart rolling, but the same shove applied to a parked car will achieve almost nothing. The car has more mass, and thus more inertia to overcome. This law quantifies the intuitive feeling we all have about effort and result. It gives us the mathematical machinery to go from a qualitative hunch, "This will be hard to move," to a precise prediction. It tells engineers how much thrust a rocket needs to break free of Earth's gravity, and it tells you how much brake pressure you need to safely stop your car. Then comes the third law, perhaps the most famous and yet most frequently simplified of all. For every action, there is an equal and opposite reaction. This is not merely a saying about karma. It is a concrete physical reality. It means forces always come in pairs. When you jump off a small boat onto a dock, the boat drifts backward. You applied a force to the boat to propel yourself forward, and the boat applied an equal force back on you. When a rocket engine fires, it hurls exhaust gases downward with tremendous force. Those gases, in turn, hurl the rocket upward with that same force. You cannot touch without being touched. You cannot push on the universe without the universe pushing back. This law teaches us about the interconnectedness of all things. No object is an island. Every action is part of a dynamic, balanced conversation of forces. But Newton's crowning achievement was his law of universal gravitation. This was the grand unification. He proposed that every single particle of matter in the universe attracts every other particle with a force that depends on their masses and the distance between them. The apple falls because Earth's immense mass pulls on it. But crucially, the apple also pulls on the Earth with an equal force. The Earth hardly moves because its inertia is astronomically larger, but the force is mutual. And most breathtakingly, this same gentle force, weakening with distance, but never vanishing, holds the moon in its curved path around Earth, and Earth in its path around the sun. It is the great cosmic glue. Suddenly, the universe made sense on a scale before imagined. The heavens were demystified, brought under the same rational umbrella as earthly events. Yet, for all its power, Newtonian physics left a profound mystery at its heart. Newton could describe how gravity behaved with incredible precision, but he could not explain why. What was the mechanism? How could the sun reach out across 93 million miles of empty space and pull on the Earth? He famously refused to frame hypotheses on this point, admitting he did not know. This action at a distance was a ghost in the machine, a puzzle that would lie unsolved for over 2 centuries, waiting for another mind to pick it up. That mind would belong to a young patent clerk named Albert Einstein, who would once again revolutionize our understanding by proposing that gravity is not a force pulling through space, but a curvature in the very fabric of space and time itself. But that is a story for another day. Newton's legacy, therefore, is more than a set of equations. It is a paradigm shift. He showed us that the universe is knowable. He replaced mystery with mechanism, and superstition with predictability. He gave us the first complete toolkit for decoding physical reality. The challenge in learning physics today is not the complexity of his ideas, but our failure to present them as what they are, a thrilling narrative of discovery. When we learn Newton's laws, we are not just memorizing rules for an exam. We are learning the opening verses of the epic poem of existence. We are being handed the key to understanding why the world works the way it does, from the swirl of milk in your coffee to the majestic dance of galaxies. Physics, at its core, is the story of us of a curious species learning to read the operating manual of the cosmos, and it all begins with a simple, powerful realization that the same principles bind the fall of an apple to the orbit of the moon, forever uniting the heavens and the earth in a single, elegant, and profoundly beautiful system. Thanks for watching, and if you enjoyed this journey into the story of science, be sure to subscribe for more.